Today I want us to talk about the squeeze theorem following on the rules of limits that we did in in lecture 29. And basically, I will try and first talk about a little bit of theory around this and then try and analyze a few cases, and then we can do some examples. The examples, I want us to have as many examples when it comes to the squeeze theorem. Maybe after these examples, someone might actually grasp the content of what are we actually doing in this particular lesson. So basically, squeeze theorem is very simple. It's just saying that suppose that you have f of x, g of x, and h of x. Suppose that these are functions such that whenever x is near, I usually use near or close to a or near a, such that whenever x is near a, let me put this near a, or x is equal to a, except possible at x is equal to a. This happens, so you have g of x, and g of x is always less than f of x, and f of x is always less than h of x. So basically here I have three functions such that f of x is in the middle of these two, close to a, but it might happen that at a this is not defined, or maybe something happens, but as long as close to a, this is happening. And when I actually take the limit as x approaches a of g of x, right, I get some value L, and this L is the same as the limit as x approaches a of h of x. Remember, because this is always below this function, and this function is always above this function, but the limit of this function and the limit of this function are the same, the squeeze theorem is saying then the limit of the middle function as x approaches a of the middle function f of x must also be equal to L. The reason is this: if this value is 1, for instance, and this one is 1, this value here is also forced because the value between 1 and 1 is 1. In this particular case, we generalize if this is actually approaching L and this is approaching L, the value between L and L is actually supposed to be L, the value between L and L. Let's try and give an illustration of what I actually mean by this. Let's draw the function here, f of x. Let's draw the function. So what we are actually saying here, if let's say this function of ours, suppose I have a nice function here which goes nicely like this, and then maybe it starts coming down and then it goes all the way, and this function is our f of x. And I know that what I really wanted to find out here is that I wanted to find the limit as x approaches a of this particular function here, right? As I'm getting closer to a, or if I were to pick a value that is so close to a and look at it output there, what will be the value? In most cases, you will find out that it is actually hard to find the limit of this function by just approaching it straightforward. Like you just approach it and then you say, I want to find the limit of this function. Then what we actually wanted to do now, I wanted to find a function such that this function here is always above or equal to this function, and then it goes and all the way up. And at this point here, this function here, I want to call it h of x. So as long as I have a function that is always above this function of interest here, f of x, and I have another function here that is always below this function of interest, f of x, I'm going to call this function g of x. So I have this function that is always above and this function that is always below. Then the limit of this function, if the limit of this as we're approaching a is the same as the limit of this function as we're approaching this particular value a are the same, then whatever this is, the limit of this, it must be squeezed to be the same value as the limit of these two functions. I have a point here of the meeting point here. The reason I have this meeting point here is because at a, I want the limit of g of x and the limit of h of x to actually be the same. So these two functions must be getting close to the same value there. That's what the squeeze theorem is actually saying, that when I'm taking the limit as x approaches a of this function g of x, look at g of x, because as I'm getting there, that is supposed to be the same as the limit as x approaches a of h of x. So these two functions must have the same limit. And because this function is always in the middle, it must also have the same limit as these two, x approaches a of f of x. So if you wanted to find a limit of a function, mostly, because in most cases you will find out that this one is the given one, but when it comes to now h and g of x are the functions that you actually need to find, and those functions should not be just random functions. It should be functions that are making this particular function f of x in the middle. So the task for the squeeze theorem is to find those functions. It's always find these two functions that are bounding this function, and those two functions must actually be going to the common point. Let's take some examples here and see what we can actually get out of this. Suppose that the question is saying evaluate, right, the following, I'm just gonna say that the following are limits using the squeeze theorem. So I will start with number one. Number one, we have the limit as x approaches 0 of, x squared of sine of 1 over x. So how do we end up finding the limit of this particular function here? Take note of this. The first thing that we usually end up doing when I'm plugging, I usually start with by plugging. So if I'm plugging here a 0, I will end up getting a 0, right? And if I'm plugging in a 0 here, I will get 1 over 0, and now I end up getting something that is undefined. And now I'm taking something undefined and I'm plugging it inside the sine. So I don't know what is happening. I am not getting a 0 over 0. I am not getting a number. I am getting something that is, I'm not getting a 0 over 0. I'm also not getting a number over 0. And secondly, I'm not getting a number, just a number here. So how do I actually evaluate this limit using the squeeze theorem? The questions usually specify use squeeze theorem, but in a nutshell, you usually follow the steps as I've said. Plug in. If you are getting a 0 over 0, you know what you need to do. If you are getting a number over 0, you know what you do. And if you are just getting a number, then you know that the laws that have been applied is the rules of limits. And if those things are not actually working out, then you have to try the squeeze theorem. There are other ways to do this, but for now we are following these particular principles. Now, let's look into this. Can we actually plot this whole thing? The answer is not at this stage of the course. You cannot really plot this whole thing. Maybe later in the course, you might be able to plot and find out how does this function actually look like. But beside this whole thing here, I know that if I have sine of theta, if I have a function y is equal to sine of theta, this function here usually looks something like this. So it goes up, it comes down, it goes down, it comes up, it comes down, and this value here is 1, and then this value here is going to be -1. So the range of this particular function here is -1 is always going to be less than or equal to y, and y is always going to be less than or equal to 1. So that is actually the range of this function. So I know that whenever I have sine of theta, this, whatever the value that I will get when I'm plugging in a theta here, I will always get a value that is below 1 or equal to 1 or above -1 and above or equal to -1. That's what usually happens, or the range of this function. That's what we actually know for sine theta. It doesn't matter what is the value of this theta here. So whenever I have sine of theta, I know that it's always going to be below these 2 points whenever I have some sine of theta. But in this case, I have 1 over x. 1 over x, take it as a theta, so whatever the value that I will get of sine is always going to be between these 2 points because of the plot that is oscillating between -1 and 1. So looking into this, if I were to take an x squared, if I take a -1, I plug it there and I square it up, it's going to be positive. A positive number, I plug it there, I square it, I'm still going to get a positive thing. So if I were to multiply this whole thing by x squared, I will end up having minus x squared, right? So it's going to be x squared times this is going to be x squared, and then this one here, because I have to do everything throughout, so I will end up having x squared times sine of 1 over x, and then I will have x squared here. Now, if you look into these functions here, x squared, which I multiplied by, is always going to be positive. So an x squared is always be positive, so the inequality is not going to be reversed. So the inequality is still going to be the same because x squared is positive. Now, if you look into this now, I take this function here as my g of x, this whole function, and this function here I am going to take it as my h of x, and this middle function here I am going to take it as my f of x. So I have found two functions that are bounding this whole function here, which is this whole thing. So in this particular case, we found those functions by knowing the range of a sine function, that it is between these two, and because this part was missing, I multiplied it through and I got these two functions. Now the next thing that I need to find out is, looking into this value here, I want to find out what is actually the limit. So I'm going to find the limit as x approaches 0 of minus x squared, which is this g of x. Now, how do you evaluate a limit? First, you plug in and see what you're getting. So if I am plugging in here, what I am actually getting is actually a minus 0 squared, which is just a 0. So that is actually my limit because I can plug in and get the output. Now, if I am taking the limit as x approaches 0 of x squared, the first thing that you do, you plug in and see what you are getting. So if I'm plugging in a 0 here, I'll get a 0 squared, which is just equal to 0. So this 0 here implies one thing here, that the limit as x approaches 0 of minus x squared is equal to the limit as x approaches 0 of x squared. Knowing that x squared minus x squared and x squared are actually making this function just abounding this function so that it does not go anywhere. And I know that those two are equal and they are equal to 0. This simply means that you can conclude this. You can just say that, therefore, by the squeeze theorem, the limit as x approaches 0 of x squared times sine of 1 over x is just equal to 0, because this function is always in the middle of these two functions. So if this is getting a 0 and this becomes a 0, then the number between 0 and 0 is only 0. So this one can be squeezed to be 0. There is no other way. Let's try another example here. We have number 2. Number 2 is saying, evaluate. What did I do now? Number 2 is saying, evaluate the limit as x approaches 1 of f of x, right, using the Squeeze theorem. Using the Squeeze theorem, given that 5 is always less than or equal to f of x, and f of x is always less than or equal to x squared plus 6x minus 2. So here I am already given the function here. I'm given this function here as g of x is equal to 5, and then f of x, we don't know what it is, but it is given that it is always less than or equal to this function, which I'm going to call it h of x. Now what I'm going to do here, I will look at the limit as x approaches this value here, which is 1, of g of x, which is 5. And the limit of a constant, because there is nothing to plug, we don't have a place to plug in, we know that the limit of a constant is always that constant. Now if you look at the limit, look into this. If you look at the limit now as x approaches 1 of h of h of x, which is x squared plus 6x minus 2, what are we actually getting? The first thing is always plug in and see what you are getting. And in this particular case here, there is a place to plug in. So when we're plugging in, we get a 1 squared plus 6 times 1 minus 2. So here 1 squared is 1 plus 6 times 1, which is 6. So 6 plus 1 is 7. 7 minus 2 is going to be a 5. So this one is the same as the limit as x approaches 1 of 5. Now, if you look into this, now we have the limit as x approaches 1 of g of x equal to 5, and this limit is the same as x approaches 1 of h of x. So, because h of x is always above f of x, and f of x is always above g of x, if this one is 5 and this one is 5, this one is forced to be a 5, you can just conclude it. Therefore, I can say that by the Squeeze theorem, we have the limit as x approaches 1 of f of x is forced to be a 5. That's it. Now, in most cases, just by saying by the Squeeze theorem, you get some mark. And then some marks are also allocated on the steps above. Right. Let's look at number 3 here. Number 3 is saying evaluate this limit. So I want you to evaluate this limit as x approaches 0 of x to the power 4 of sine of 7 over x. So how do you deal with this function here? So I know that I have my f of x in the middle, and I want my h of x here, and I also want my g of x here, such that when I'm taking the limit as x approaches this number here, 0 of g of x is equal to some value L, and this L is the same as the limit as x approaches 0 of h of x. So what is this function? Because your goal with the squeeze theorem is to find this function and that function such that the limit of these two are the same. That is your goal. This one here is given there. Now, if you look into this here, we know how to deal with this function here. You can draw it because this number is even, so the shape of this function looks exactly as that of a it looks like it has the same shape as a x squared, because this and that is even. It's just that this one is more relaxed along the x-axis. So if I have this function now and that function, then it will be easy for me to find the limit, because I'm going to squeeze that to this number, which is equal to that number. Now, how do we end up finding those two functions? You look into this function here, this function f of x, because this is going to be your f of x, and you look and find out what how can you deduce some information from this function so that I get some info or some insights on this function and that function. The good way to start is to look at what is the range of that function, what is the range of that function, and work around it. So suppose we were to look at x to the power 4. X to the power 4 looks something like this. Right? So if you look into this function here, its range is going to be y is greater or equal to 0. So it goes all the way up to infinity. So this one here cannot really give me more insights on what this function could be and what that function could be. But if I look into this one here, I know that the range of this is kind of bounded on both sides. So I can start with it and work my way up. And then I will deal with this one next. So let us actually try and see. You know that whenever you have sine of theta, let's say you have y is equal to sine of theta, this function will never be above 1. Whatever I plug here will always be less than 1, and at the same time it will always be bigger than minus 1. So it's always going to be in between minus 1 and 1. But in this particular case here, the theta that is given is 7 over x. Whatever the value I plug here, I will get a value in between those two. I don't know for now what is the value, but I know that it is in between minus 1, this is 7, minus 1 and 1. Now let's take a look into this. But if you go back here, I have this function multiplied by that function. What do I need to do in the middle part so that I end up having this part here, or end up introducing this part? I need to multiply this thing so that I end up having x to the power 4. But if I'm multiplying this only, these inequalities may not be preserved. So if I want to multiply a certain part, I need to multiply throughout. So when I'm multiplying throughout, I'm multiplying this by x to the power 4, I'll get minus x to the power 4, and then multiplying this whole thing, I'll get x to the power 4 times sine of 7 over x, and I'm multiplying this, I'll end up getting x to the power 4. X to the power 4, looking into this function here, is always going to give you positive values. Therefore, multiplying throughout is not going to change this inequality here, because x to the power 4 is always positive. So the inequality directions are preserved. Now, then once we have done this whole thing, I need to find the limit of that. I need to find the limit of that. How do I find the limit? Because I want to take the limit as x approaches the number we're given here, which was x approaches 0. So as x approaches 0 of minus x to the power 4, the first thing that you do is I want to first plug in and see what I'm getting. So I will get minus 0 to the power 4, which is the same as just minus 0, which is the same as 0. If I'm looking now for the limit of this bound here, or this function here, I will get, as x approaches 0, of x to the power 4 is going to be the same as, I'm plugging here, I will get 0 to the power 4, which is the same as 0. This is the number, therefore it has to be the limit there. So now that I have these two things, I have this is going to 0, this one is going to 0, the number between 0 and 0 is supposed to be 0. Therefore, by the squeeze theorem, I have the limit as x approaches 0 of x to the power 4 times sine of x over 7 over x must also be equal to 0. That's it. You don't have to worry about so many things. We have that. Let us now look at another example, number 4. The limit, this is not the good limit. I want us to find the limit as x approaches 0 of x squared and then cosine of 5 over x. All you need to do here, we still do the very same thing. I know that the cosine function of theta, whatever the value is inside, it's always going to be less than or equal to 1, and this is always going to be less than or equal to minus 1. It doesn't matter. Now, I have an x squared here. I'm going to multiply by x squared throughout. I will get minus x squared less than or equal to x squared times cosine of 5 over x less than or equal to x squared. And then after that, I can take the limit as x approaches 0 of minus x squared less than or equal to the limit as x approaches 0 of x squared cosine of 5 over x, and then I can take the limit here as x approaches 0 of x squared. Remember that I've just done the same thing of taking the limit of this and the limit of that, but now I'm just doing it in a series of steps. It's more systematic now. We're trying to be a little bit cleaner. And now if I am plugging in here, I will end up getting a 0 is less than or equal to the limit as x approaches 0 of x squared cosine of 5 over x, and this one is less than or equal to, if I'm plugging in a 0 here, I will end up having a 0. So this number is between 0 and 0. Therefore, by the squeeze theorem, whatever the limit of this, it must be equal to x approaches 0 of x squared cosine of 5 over x. It must also be equal to 0. That's how easy this thing is. Let's try another example. These examples are nice. So I want us to find the limit as x approaches 0 of x squared cosine of 10x. You do the same thing here, that if I have a cosine, it doesn't matter what is inside there. It's always going to be less than or equal to 1, bigger than or equal to negative 1, and then I multiply by that whole thing here. I will get a minus x squared less than or equal to cosine. If I'm multiplying, I should multiply it throughout. I'm going to have x squared cosine of 10x less than or equal to x squared. Take note that the reason these inequalities are not changing is because x squared is positive. So when you're multiplying by a positive thing, the inequality is not going to change. And then after that, I'm going to take the limit as x approaches 0 of minus x squared less than or equal to the limit as x approaches 0 of x squared cosine of 10x less than or equal to the limit as x approaches 0 of x squared. And if you look carefully here, if I plug it in here, I will get minus 0 squared, which is just 0, is less than or equal to the limit as x approaches 0 of x squared times cosine of 10x less than or equal to. If I'm plugging in a 0 here, I'll get 0 squared, which is just 0. So you can just say here, therefore, by the squeeze theorem, the limit of what is in the middle here, which is x squared times cosine of 10x, must actually be also equal to a 0. So in this particular case here, you can actually see that the squeeze theorem is actually very nice and easy to evaluate. So that's what we're actually doing in number 5. Let's try another examples here. These examples are a little bit nicer. So you have 6. So I want us to evaluate the limit as x approaches a 0 of x squared sine of, I want to have 5 over x now, but I also want to add some value 1 there. Of course, we're still using the squeeze theorem here because all we really know is that whenever I have a sine of something, whatever is inside will never be above 1 and it will never be below -1. And then after that, because this x squared here is always going to be positive, so when I'm multiplying throughout, the inequality is not going to change. So I have minus x squared less than or equal to x squared times sine of 5 over x and less than or equal to x squared. Now I have this 1 here. If I need a 1, I need to plus 1 throughout. So here I will end up having minus x squared plus 1 less than or equal to x squared sine of 5 over x, and then this one here is going to be plus 1 because I plussed a 1 here. I need to plus a 1 here, and also I need to plus a 1 here. When I was multiplying, I multiplied through. Now I was adding, I add through. When you are adding, the inequality does not change the direction. Usually the inequality only changes the direction when you are multiplying or dividing by a negative number. Now I take the limit throughout, which as x approaches 0 of minus x squared plus 1 must be less than or equal to the limit as x approaches 0 of x squared times sine of 5 over x plus a 1, which must be less than or equal to the limit as x approaches 0 of x squared plus a 1. So if I plug in here a 0, I will get a 0 squared plus 1. So I'll get a 0 plus a 1, which is just 1, must be less than or equal to the limit as x approaches 0 of x squared times sine of 5 over x plus 1 less than or equal to, if I plug in here, I will get a 0 plus 1, or 1 is less than or equal to the limit as x approaches 0 of x squared sine of 5 over x plus 1 less than or equal to 1. So the number between 1 and 1 is just 1. Therefore, by this squeeze theorem, the limit that is in the middle as x approaches 0 of x squared sine of 5 over x plus 1 must be equal to 1. So basically, that's what is important about this whole thing. We wanted to find this function here. So this function is the one function that needs to be in the middle. So in the end goal, this function must be in the middle, and this limit must be in the middle. And this limit that you are getting here should be equal to the limit that you are getting this side. So if you chose functions that are not working, then you need to change functions and keep looking. So that's how you end up looking this. It's not always easy. Sometimes it's not that straightforward. Let's actually take another example here. Example number 7. I want us to evaluate the limit as x approaches 0 of x squared times sine of 3 over x plus a 2. It's supposed to be x squared over 2. Using the squeeze theorem. The first thing that you know of, I'm going to deal with this sign here. Whenever I have sine of 3 over x, this one I know that's always going to be less than or equal to 1 and always going to be above -1. and then I multiply it throughout by this positive number. So if I'm multiplying throughout by a positive number, I will end up having minus x squared less than or equal to, the inequality is not going to change because x squared is always positive. X squared sine of 3 over x less than or equal to x squared. And then now I'm gonna add these two because the end goal, I wanted this whole function to be in the middle, in other words to be my f of x. While I'm doing that, I should be getting my g of x here and my h of x. So here I will end up having minus x squared plus 2 less than or equal to x squared sine of 3 over x, and this must be added a 2 here less than or equal to x squared plus a 2. And if you look carefully into this, the next thing is I want to find the limit as x approaches this number here, which is 0, of minus x squared plus a 2. It must be less than or equal to the limit as x approaches 0 of x squared times sine of 3 over x plus a 2 must be less than or equal to the limit as x approaches 0 of x squared plus a 2. So if you look carefully into this, when I'm plugging in here, I will get a 0 plus 2. So I'll get a 2 less than or equal to the limit as x approaches 0 of x squared sine of 3 over x. And then this whole thing, I'm going to add a 2 there, less than or equal to. If I'm plugging here is 0, 0 squared is going to be 0 plus 2 is going to be a 2. So then now this number here is between 2 and 2. Therefore, this whole thing must actually be a 2. Therefore, by the squeeze theorem, the limit as x approaches 0 of x squared sine of 3 over x plus a 2 must be equal to 2. If you don't write this, the squeeze theorem, you might end up losing some marks because we really wanted to see that you know which theorem that you are using. Sometimes you might end up getting a 0 if that squeeze is not there, because we want to see which theorem are you using. We don't want you to just assume that because of that. No, we want to know the theorems you are using. So you can say by the squeeze theorem. Even if the thing is saying use squeeze theorem, we want you to know that you know how to use the squeeze theorem. So you need to mention that after this stage whereby you have a number that is equal to a number, the following thing is the squeeze theorem, and then you get that. Now, I am not going to proceed with so many examples like this because you can, let's say I'm giving you number, let's say number 8. We're coming from number 7, right? And I want you to find the limit as x, or evaluate the limit as x approaches 0 of x squared of sine of 9 over x minus 2. You know that using the squeeze theorem, so if you want to use the squeeze theorem here, I know that you will end up having your sine of 9 over x, and then this is less than or equal to 1, and this one is bigger or equal to minus 1. And then after that, you multiply it through by what is in front of this. So you end up saying, because this one is always positive, so I am actually going to end up having minus x squared, and then is less than or equal to x squared times sine of 9 over x, and then this one is less than or equal to an x squared. So if you look carefully on this, I might then realize that I have a minus 2, so I'm going to separate a 2 throughout. So I'm going to have a minus x squared minus a 2 less than or equal to. The reason I'm separating these two, I want to end up with this whole function here in the middle. So I will end up having that I have x squared sine of 9 over x minus a 2 less than or equal to x squared minus a 2. And then I take a limit throughout and see what I'm getting. If this the limit of this and the limit of that is not the same, then I need to change the function. It doesn't mean the squeeze theorem does not work or the limit of this does not exist. No, you don't say that the limit of this does not exist. You need to change the functions that are bounding this whole function and try again. That's what you need to do. And then here I will end up having minus x squared minus 2 less than or equal to the limit as x approaches 0 of x squared sine of 9 over x, and minus 2 less than or equal to the limit as x approaches 0 of x squared minus a 2. So if I'm plugging in a 0 here, I will get minus 0 just 0, and then I'm left with minus 2 here less than or equal to the limit as x approaches 0 of x squared sine of 9 over x minus a 2 less than or equal to, if I'm plugging in a 0 here, I will get a 0 minus 2, which is just minus 2. So looking into this number here and that number there, these two numbers are equal. If this number and that number are equal, then I can use the squeeze theorem. If these numbers are different, then I cannot use the squeeze theorem. I need to choose different functions or find another method to actually bound this function. So you say by the squeeze theorem, the limit as x approaches 0 of x squared times sine of 9 over x minus 2 must also be this number, which is the same as that. So it must be 2, minus 2 actually. Now, let's go to some of the examples that are very interesting. These examples would be so much of an interest that it needs you to actually pick your brain up. Suppose now I am giving you this. I'm saying evaluate the following limit using the squeeze theorem, and this limit goes like this. They'll find the limit or evaluate the limit as x approaches 0 of x times sine of x. Now, how do we end up using this? Let me try with the mistake that most of us would actually do. The first thing that we can do is, someone might say that, I'm going to write this with a black, sine of x, right, is less than or equal to 1 and less than or equal to minus 1. And I would say that that's actually true, no problem. The next thing someone might say is that if that is the case, let me use this one here, then minus x, multiplying this whole thing by minus x, should be less than or equal to sine of x, and this times x, because I'm multiplying this whole thing, and then this should be less than or equal to x. Let's look into this. Suppose that my x was actually a negative number. My x was actually a negative number. So if I were to multiply -1 by a negative number, I'll get a positive number here. This positive number can never be less than a negative number because my x was negative. So this actually will actually be a wrong way to go, because these inequalities are not going to be preserved like this. Because now once you multiply by x, if x is negative, the inequalities will go in a different direction. Now, how can we make sure that our inequalities are actually not in a bad direction and this is actually correct? Because now, in this particular case, this is actually not true. S is actually not true. It's wrong. So going in this particular way would actually compromise your way of actually solving the problem, because if x is negative, then multiplying by this will actually give us a problem. So we cannot go through that route. Even if, let's say, you try and split it, you will see what's going to happen. You will see what is actually going to happen. Now, this is the correct way to actually do this. I am going to say, suppose, I'm not going to use this color anymore. If x is greater than or equal to 0, then multiplying this whole thing is not going to change the inequality. So I will end up having minus x is less than or equal to x times sine of x, and this one is less than or equal to x. And now this one, now given this condition, it is correct. And then the next thing now is, remember that we are still only dealing with this condition here. So we are starting at the positive side of 0, or the side on the right of 0. So the limit as x approaches 0 on the right, because this is on the right of 0, of minus x must be less than or equal to the limit as x approaches 0 on the right of x times sine of x, and this one must be less than or equal to the limit as x approaches 0 on the right of x. Now, if I were to plug in 0 here, I would end up getting 0 is less than or equal to the limit as x approaches 0 on the right of x sine of x, and this is less than or equal to, if I were to plug in 0 here, I get a 0. The number between 0 and 0 is just 0. Therefore, by the squeeze theorem, I have the limit as x approaches 0 on the right of x times sine of x is equal to 0. Now, what would happen if now I were to change this and look at when x is less than 0? So I am going to say, if x is less than 0, then, and I know that minus 1 is less than or equal to sine of x less than or equal to 1. Multiplying this whole thing by x, I will end up getting minus x, but because this x is less than 0 is negative, multiplying by something negative is going to reverse the inequality. So I will end up getting something like this, but I'm still going to have x sine of x, and then here the inequality will go like that. 1 times x. So we'll end up having that. Or rewriting this is just saying x now will be less than or equal to x times sine of x, and this should be less than or equal to minus x. But this is not that important, because this and that means the same thing. It's just that now I wanted the inequality of less, not greater. So it's not bringing any new information. I can just proceed in this particular format. Take note that I am using this, which means we're on the left. So if I were to take the limit as x approaches 0 on the left of minus x, this must be greater than or equal to the limit as x approaches 0 on the left of x times sine of x, and this must be greater or equal to the limit as x approaches 0 on the left of x. Plugging in here will get 0. 0 is greater or equal to the limit as x approaches 0 on the left of x times sine of x, and this must be greater or equal to, plugging in a 0 here, I get a 0. So you can see this. Therefore, by the squeeze theorem, the limit as x approaches 0 on the left of x times sine of x is equal to 0, because the number between 0 and 0 is just 0. So I've already found this, and I know that the limit as x approaches 0 on the right of x of 0 on the right of this, so equal to 0. Therefore, because on the left of 0 I get 0, on the right of 0 I get 0, then the limit as x approaches 0 of x times sine of x must also be equal to 0, because if this happens, if you remember when you're doing one-sided limits, if this happens, this needs to happen and that needs to happen. If these two happen, then this needs to also happen. Now, let us actually look at a different example, because you have noticed here that what we actually did was we started like this, but instead of just multiplying by x, we realized that actually x can be both positive or negative. When it is positive, inequality is not going to change. When it is negative, then inequality changes direction. So we ended up having some nice things here. Now, let us look at some of the important things that one person can actually do. I want us to switch gears a little bit now. At this point here, you can see that we are actually paying every little detail of the function. If you want to be good with Squeeze Theorem, first make sure that you are good with our basic functions. You see, the basic functions that we studied are the functions that you need to be good at. Once you are good with those functions, you will know their domains, their range, and some of the basic properties that we did. Make sure that you understood them very well, because if you don't, then Squeeze Theorem becomes hard. But it's not hard, it's not so hard that it cannot be done. The only thing that will be hard now is to pick the functions, because you can see that in this previous example that we started by saying that I know sine is in between these two, and now I have to deal with this. But now I needed to know that if this one is positive, then I know that the inequality is going to reverse, and also if it's negative, and I also know this function is capable of being positive and negative. In the other cases, this one you knew that its range is always starting at 0, so this one is always going to be positive. But here also the understanding matters. Let's actually now shift some gears. I want you to evaluate these following functions. I evaluate this following limit. Evaluate the following limits. So I am going to look at the limit as x approaches 0 of sine of x now divided by x. That's the first one. The second one is I want you to find the limit as x approaches 0 of 1 minus cosine of x divided by x. And then I want the third one to be find the limit as x approaches 0 of 1 minus cosine of x divided by sine of x. I want you to evaluate that. I also want you to evaluate the limit as x approaches 0 of sine of 3x divided by sine of 4x. I also want you to evaluate the limit as x approaches 0 of e to the power x minus 1 divided by x. So this limit here, I'm gonna circle them red. This limit, you need to make sure that you always understand it and you can always remember what is the value of this limit. The limit of this is supposed to be, the answer is supposed to be just 1 for this. So the answer we're supposed to know is this is supposed to be 1. And you also need to know the value of this limit here, that it is equal to 1. This limit and that limit, they are very important in calculus. And this limit here, you also need to know it will come, we'll need it in the course when we are dealing with derivatives. You need to know it by heart that this limit here is equal to a0. So know these limits by heart. Make sure that you know them. I don't know if you're gonna cram them or you're gonna understand them. The choice is yours. That make sure that you know these basic tree limits. I am going to try and talk about this one. This one can be found using different techniques or use this one, and this one can be found using this one and that one, and this one can be found using the understanding of that. And of course there are other limits, but I want you to know these limits, that this is equal to 1, this one is equal to 1, this one is equal to a0. Let's try and see if we can actually succeed in solving these limits. Let's see. The first one is saying this. We wanted to find, this is number 1. Number 1 is saying we wanted to evaluate the limit as x approaches 0 of sine of x divided by x. If you look into this, based on what we have studied so far, if I am plugging in a 0 here, sine of 0 is 0. If I'm plugging in a 0 here, I will get a 0. So I will get a 0 over 0. There are two methods for a 0 over 0 that we have studied so far. The first one is saying factorize this. But if you look at sine, we can't factorize it. There's nothing to factorize there. So because it cannot be factorized, the next thing that we need to do, we need to rationalize this function. But what are we going to rationalize here? Because if we're rationalizing, we'll still either gonna end up with something that have a cos like this, but we still haven't dealt with. So rationalizing is not going to work, and factorizing is not going to work. The two other things that we can try is using L'Hopital's rule, but we haven't studied it, and plot this function, but we can't plot it. So the next thing that we need to try, because we cannot use rules of limits here, because the limit of this as x approaches 0 is 0, so we don't want a limit in the denominator to be a 0. And if we are trying to split this, find the limit of this and the limit of 1 over x, 1 over x does not exist, so we cannot find that limit, because this one we know is going to be 0, but 1 over x is not going to exist. We are forced now, because we know the squeeze theorem, we are forced to use the squeeze theorem. How do we end up using the squeeze theorem? The squeeze theorem is not hard for a function like this. I will give you a quick overview of what we're going to do. The first thing needs us to understand sine of x. So if you understand your sine of x, you will plot a function like this, and you know that sine of x behave in this particular format. I am going to, this is going to be, let me move this, this is going to be y-axis, this is going to be x-axis. And sine of x is usually this one here. I want it to be a 1, and then here I will have a minus 1. A sine of x is going to increase all the way up until it arrives over at 1, and then it's going to start coming down all the way, and then it's going to go down, and then it's going to start going up a little bit. And then here is going to go down and then start going up all the way, and then start gonna go down again. What is important here is not all the values. I want to know that when is this gonna be 1? This is going to be pi over 2. When is it going to be negative 1? It's going to be negative pi over 2, somewhere here. And now I wanted to do something a little bit crazy here that goes like this. I will explain why am I doing this at a later stage. Now, I have drawn this function that is above the x-axis. The main goal is to find some function g of x such that this function is always going to be less than or equal to sine of x, and sine of x is going to be sine of x divided by x, and this is always going to be less than or equal to g of x. So that the limit as x approaches this value here of 0 of g of x must be equal to the limit as x approaches 0 of h of x, so that if these limits are equal, then the limit that we're getting here should be the same as that. So because this function is going up and down, it's really hard to find the function. Remember here what we are trying to do. The end goal, we want to end up with a function that is actually like this in the middle. But now we only know how to draw sine and the information of sine. So at this particular point here, which is x is equal to 0, I want to find a function that is always gonna be below this function and the other to be always above this particular function. Now, what is the next function that I can actually think of here? If I were to think in terms of functions here is one thing. Another function that I want to think of is this function here, which is this function which is y of x. So this one here is f of x. I don't want to use f of x. Is y is equal to sine of x. Now, I wanted to plot this function here in the denominator. Right. So if I'm plotting that function, I know that when this is equal to 0, so it's going to pass through that point. So it's going to pass somewhere like this. It's going to go all the way like this. This one is y is equal to x. And it's going to go all the way like this here. Right. So this is y is equal to x. Now, I need the third function here. Now, the function that I am actually looking out for here is a function that is actually having sine in it, and also it can be written in terms of a fraction here, if possible. If we can't get that function, of course, we will end up having to try and use polynomials, and also try maybe and use power functions, or also try and use some other important functions. If I were to use cosine function, right, a cosine function is going to start at this point here. I want a function that is going to pass through this point, which is the point of interest here. X is equal to 0. Why is that so? If I am plugging 0 in this function, I am getting a 0. So this function is passing through the origin. I want the third function to also pass through the origin. Now, if let's say I try now and use my x squared. X squared here, let's say I am going to actually have an x squared, s squared here. I have an x squared. Suppose I have an x squared. If I have an x squared cannot always be, if let's say I have an x squared will look like this. Something like this, right? It's going to look something like that. But now, if you look at x squared here, you will notice something here, that sine of x is always less than this function here, right? If let's say we consider this region from 0 up to this pi over 2, sine of x is always below or equal to y is equal to x. That is fine. But when we are considering this x squared here, you will find out that actually an x squared is always below sine, but it starts to be above all these functions when we at some point as we are getting closer to pi over 2. So we want a function that is going to behave in a same way like this, that if I am moving, let's say I'm moving from this point up until that interval here, I can say that this function is always going to be either above all these functions or either below this function or in the middle of these functions. So we decided that let's not use this one here because it's creating so many problems for us. I will try maybe later after I'm done with this and see what is actually going to happen if you chose this function. Now, can we actually choose another function, because cosine is not working, and this quadratic function, or the power function x squared, has some reasons for it actually not to work. Now, how can we actually deal now with this problem that we're actually having here? So what we do is we try to say, let us decide to forget about what is happening so much away from I'm gonna just do this, so much away from this point of interest, which is x is equal to 0, and just focus on this particular interval here, which is close to 0. This one is still y is equal to sine of x. Now let's try another function not so far from sine. We can try tan of x. The reason we are trying tan of x, y is equal to tan of x, is because this is the same as sine of x divided by cosine of x. So we still have sine built in it. And also another thing that is good about this that we can use to try is because it is a fraction and we also have a fraction. So we can try this one, and if it's not working, we will change it and look for another function. So looking at tan of x, we know that tan of x is actually increasing so faster than both of these functions, but it will never, because when I'm plugging pi over 2 is 90. If I'm plugging pi over 90 here, 90 degrees in cosine, you get a 0, and this is going to be undefined. That is why a tan function will never touch that. And also this side is gonna go all the way and then start going down, but it's also not going to touch minus 90 degrees. So a tan function, looking from 0 up to pi over 2, a tan function is always above these two functions, and looking between negative pi over 2 and 0, a tan function is always going to be below these two functions. How are you supposed to know all of these things? If you actually did the homework and you drew sine function, like I gave you a homework before, and a cosine function, and the sine function, the cot function, and cosecant and sec function. Now let's use this function and see what we're actually getting here. So if now I am looking at from 0 is less than or equal to x, and x is less than or equal to pi over a 2, I know this is actually happening. I'm going to use a different color. Red, I think, is going to be fine. So if I'm looking into this region here, I know that this is the region here. Sine of x, let me start with this. In this particular region, x is positive. So it's something that you need to know. So sine of x, this function here, is always going to be less than x. So it is less than or equal to x. Because x is positive, so when I'm dividing by x on both sides, it means that now sine of x divided by x must be less than or equal to 1. Take note that here the inequality did not reverse because x is positive. So I'm going to call this equation 1. And then if I look into tan of x here, I'm going to use a blue here. Tan of x is above. Okay, let me do this instead. If I look at x, at this function y is equal to x here, y is equal to x, y is equal to x, this function is always below tan of x, right? Which means that x is actually less than or equal to sine of x divided by cosine of x. So if you look into this particular function, you'll find out that I have x cosine of x is less than or equal to sine of x. Let me explain. If you look here in this quadrant between 0 up to 90 degrees, which is the first quadrant, a cosine function is always positive because all of them are positive in the first quadrant. 0 to 90, they are all positive. So when I'm multiplying throughout by cosine of x, then the inequality is not going to reverse. It's just that this is going to go that direction. X is also positive, so when I'm dividing by x throughout, the inequality is not going to change, and we're going to be left with a cosine of x is less than or equal to sine of x all over x. I'm going to call this one equation 2. Now, I am going to combine equation 1 and equation 2. Combine equation 1 and 2, or from equation 1 and 2. This is what we are having. The limit as x approaches, we are going to 0, of course, but now we are only considering from 0 up to pi over 2, only this positive side or on the right side of 0. So we need to have a plus here. This plus is saying on the right. And then this is what we're actually going to end up with. But let me first deal with this thing. Where is this now? If you look into this, I have my cosine of x. Cosine of x is less than or equal to sine of x divided by x. And this sine of x divided by x is less than 1. So this whole thing is less than or equal to a 1. Which means now, if I take the limit throughout of cosine of x, this must be less than or equal to the limit as x approaches 0 on the right of sine of x over x. And this must be less than or equal to the limit as x approaches 0 of 1. If I were to plug in 0 in cos of 0, we know that it is 1. So 1 must be less than or equal to the limit as x approaches 0 of sine of x divided by x, and this must be less than or equal to the limit of a constant is that constant. Therefore, by the Squeeze theorem, the limit as x approaches 0 on the right of sine of x divided by x must be equal to 1. Now, we need to deal with the left now. We have dealt with the right. Suppose now I am dealing with minus pi over 2 less than or equal to x, and x is less than or equal to a 0. So we are in this region here on the left of 0. If you look here, the tan function is less than, or is below means less, below than y is equal to x. Remember that this is tan, this one is y is equal to x. So I have a tan function of x is less than or equal to x, and this one we know that we have sine of x divided by cosine of x. Tan is the same as sine divided by cos, less than or equal to this. Now I also know that x in this particular region is negative, right? So if you look carefully into this, I want you to see this. If, let's say, I look at this cosine here. Let's start with the cosine and then we'll deal with x. In this region here, from 0 up to this negative 90 degrees, having a negative angle, it means that instead of rotating clockwise, you went anti-clockwise. Instead of going anti-clockwise, you went clockwise. So 90 degrees minus 90 degrees is the same as 270 degrees minus 90. So looking for values that are in between 0 and 270, that is actually the fourth quadrant. The fourth quadrant is the cos is positive. So the cosine function is positive in the fourth quadrant. So multiplying by cosine function, dividing by it, the inequality is actually not going to change. So I will end up having sine of x less than or equal to x times cosine of x, because this is always going to be positive in the fourth quadrant. Now, if you look into this here now, what we can actually see now is that I have an x here, and the end goal, I want to end up having x in the denominator of sine. So I divide by sine on both sides, by x on both sides. So I'll end up having sine of x divided by x, and then I'm left with cosine of x now. Now, take a look into this. In this region between 0 and this angle here, our x is actually negative, right? So our x is actually negative. So if x is negative, multiplying or dividing by a negative angle changes inequality sign. So the inequality is going to go that way, and then I'm going to call this equation 3. Now, if again you look into this region, we talked about tan and x. Now we have to talk about x and sine. So if I look at, I'm going to change this. I'm looking at now sine. Sine of x is always bigger or equal to x because it is above. Let's look into this. Sine is this one. It is above this function y is equal to x. So sine is bigger than it. So we have this nice thing here. Now I divide on both sides by, I have sine of x, and then I divide this whole thing by x, and then that side will end up having a 1 if I'm dividing x by x. So I end up having a 1. Now, if you look into this, all right, remember that here the inequality was going this way, but my x is negative, so the inequality needs to reverse the direction. So because the inequality is reversing the direction, I'm going to call this equation 4 and combine these two and say from equation 3 and 4, what am I actually having? I am actually having the fact that whenever I have sine of x divided by x, so I have sine of x, it is less than 1. So this is less than 1. Whenever I have sine of x, this sine of x is bigger than cos. So this one is going to be bigger than or equal to cosine of x. So using these two equations here is actually saying that, yes sir, you can actually take the limit as x approaches 0, but now we're on the left of cosine of x less than or equal to the limit as x approaches 0 on the left of sine of x divided by x less than or equal to the limit as x approaches 0 on the left of 1. One thing for sure, what is the limit of a constant? It is that constant less than or equal to the limit as x approaches 0 on the left of sine of x divided by x. And then here, if I were to plug in a 0 here, a cosine of 0 is just 1. So by the squeeze theorem, we can say that actually the limit as x approaches 0 on the left of sine of x divided by x must be equal to a 1. And because this one, I can just say, therefore, the limit as x approaches 0 on both sides of sine of x must also be equal to 1, because on the left we got a 1 and on the right we got a 1. Suppose for some reasons we were so high and we decided to go with something different. Let me also explain this. This is also another y now. If let's say here, can you see that in this side, suppose that someone decided to do this. I'm gonna try and be quick. If you understood this one that I did above, forget about this, because I'm just trying to see if someone decided to follow this one is sine of x, and someone decided to go like, I'm gonna end up with this, and this one is y is equal to x squared. Go this way. This function is, this side is bigger up to this far. We have 0 here, and then someone decided to do this instead, and this instead. So we end up having, this is y is equal to x, this one is y is equal to sine of x, this one is y is equal to x squared. When 0 is less than or equal to x and x is less than, I'm gonna call it some value up to some point here where they intersect. So this is going to be my a. Now if I look into this, I would end up with x is bigger than or equal to sine of x, and x is going to be bigger than or equal to x squared. So if let's say now I am dividing by x throughout, I'll end up having 1 is bigger than or equal to sine of x divided by x greater or equal to some x, because when I'm dividing here, 1x will be actually gone. Now if I am looking for, I just want to give you an illustration why we cannot end up using this, the another reason. So if I'm taking the limit as x approaches 0 on the right of 1, and then this needs to be greater or equal to the limit as x approaches 0 on the right of sine x divided by x. This one must be greater than or equal to the limit as x approaches 0 on the right of x. If I'm plugging 0 here, I will end up having 0. The limit as x approaches 0 on the right of sine of x divided by x. And if I'm the limit of a constant is always going to be that constant. Now if let's say you used this, you would end up having 1 and 0 are not the same, so you cannot conclude using the squeeze theorem. That is why we cannot use this function here, which means we need to pick another function. So this is also another reason why, because we end up getting a 1 and a 0. I want this number and that number to be the same to use squeeze theorem. So having this function is not going to work. That's why we used tan. That's also another main reason why we don't use those functions. Let's go to number 2. Just few questions, just a few of these, and then we can call it a day. Right. So if let's say we want to evaluate the limit as x approaches 0 of 1 minus cosine of x all over x, how do we do it? This one is also going to be very simple, because what we are actually going to do here, I'm going to take this 0, plug it here. Once I plug it here, I get a 0. If I plug it here, cosine of 0 is 1. 1 minus 1 is 1. So I get a 0 over 0. The first thing that you try here is factorize. There's nothing to factorize here, because now we have this part here and that part. If let's say factorization doesn't work, the next thing is rationalize. So we don't know here if rationalizing is going to happen or not. The reason we're gonna try it is because we already know that the limit as x approaches 0 of sine of x divided by x is equal to 1. So we're gonna try that, hoping that we'll end up getting something of this kind that will help us to actually find the limit. But otherwise, if we did not know this, we're not going to rationalize this. We're going to try the squeeze theorem. So we try and rationalize and say, actually, this limit here as x approaches 0 of 1 minus cosine of x divided by x, what are we actually rationalizing? We have a 0 in the denominator. The numerator doesn't have a problem. So I need to cancel the part that is causing the denominator to be equal to 0. So I wanted to cancel an x, and x is, I need to cancel this x. So rationalizing this x is creating so many x's in the denominator. I don't want so many x's. I want to reduce them. So I cannot rationalize the denominator. I'm going to rationalize the numerator. How do you rationalize? You change that sign there. So you end up having to multiply by 1 plus cosine of x. Because this thing was not part of this, you divide by it again. 1 plus cosine of x. And then this whole thing here is going to be the limit as x approaches 0. When I'm multiplying this, the denominator, I am not going to simplify it. I'm going to leave it as it is. Why am I doing so? Is because I want to cancel this x. So when I'm distributing it, I don't know what I'm doing, because I want to actually cancel this x so that the problem can be reduced. So I have this x. Then the numerator, I am going to actually simplify it, right? 1 times 1 is going to be 1. 1 times cosine x is going to be plus cosine x. Minus cosine x times 1 is going to be minus cosine x. Minus cosine x times cosine x is going to be minus cosine squared x. So the cosine x minus cosine x is gone, so I need to take it out. So I have x minus 1, and then in the numerator I will end up having 1 minus cosine squared x. I divide this by x, and then I have 1 plus cosine of x. So I have this nice thing here. One person who's very smart than everyone that I know of will actually factorize this. After factorizing it, get that whole thing, and then after getting that whole thing, cancel out the common factor. Now they end up with the very same thing they are trying to solve. We are not factorizing anything here. We are just leaving this as it is, so that we can simplify and cancel this, as the main goal is to cancel this if possible. If we can't cancel it, we want to use that. So one thing that I know of is that whenever I have sine squared of x plus cosine squared of x, I always get a 1, which means that sine squared x is the same as 1 minus cosine squared x. So I already have this. I'm going to change this to that. So I'll end up having the limit as x approaches 0 of sine squared x divided by x times 1 plus cosine x. Right. Now that I have this nice thing here, one thing that you need to know is that whenever you have sine squared, you must know that you have sine of x, and then you divide by this x here. And then you also have another sine of x, because sine times sine, you get sine squared. And then in the denominator, you still have 1 plus cosine of x. Right. So if you look into this, whenever you have multiplication of two functions, I am going to consider this as one function because I know its limit is 1. And then I'm going to consider this one part as another function because I know how to deal with that limit. So I will end up having, this is the same as the limit as x approaches 0 of sine of x divided by x times the limit as x approaches 0 of sine of x divided by 1 plus cosine of x. Can you see how easy now this thing is? This one I already know that it is 1. And now finding out this limit here, I plug it in. I get sine of 0 divided by 1 plus cosine of 0 1 times anything is that anything. So sine of 0 is 0, I know. 1 plus cosine of 0 is 1. So I have 0 divided by 2, which is just 0. I am done. Therefore, the limit as x approaches 0 of 1 minus cosine of x divided by x is just equal to 0. And of course, if I were to change these two things around, and also someone might deduce that the limit as x approaches 0 of cosine of x minus 1 over x, this is also equal to 0, because if I factor out a minus 1 here, I can take that minus 1 in front of the limit and take the limit, which is equal to 0. 0 times that minus 1, I'm still going to get a 0. So this limit here is 0, that limit is 0. And another thing someone might deduce is that whenever I have the limit as x approaches 0 of sine of x divided by x, this is equal to a 1, which means that the limit as x approaches 0 of x divided by sine of x must also be equal to 1. The same thing. These two functions are actually getting close to the same value, and this is supposed to be the same. If you don't want to use this, you can just realize that actually to get this, you can just take the negative exponent of that and take the limit first, and then take the negative exponent of 1, and then you end up getting this. So this is equal to that, and that is equal to that, this is equal to that, and this is equal to that. Let us proceed to another example here. Suppose we want to find the limit as x approaches 0 of 1 minus cosine of x divided by sine of x. Now things becomes very much interesting, because I only know how to deal with the limit of 1 minus cosine x divided by x and sine of x divided by x. I don't know how to deal with this. But all you need to do here is to manipulate this function to look like what you know. 1 minus cosine of x. I'm going to divide this by x because I know its limit. Because this x was not there, I'm going to multiply by x, so that when I'm multiplying this x and when I'm cancelling this x and that x, I end up with that. But now I also divide by sine of x. This sine of x is that. This one and that one, they can cancel out to get that, but I know how to deal with the limit of this. So this is going to be the limit as x approaches 0 of 1 minus cosine of x divided by x times the limit as x approaches 0 of x divided by sine of x. So because of that, I know the limit of this is 0, the limit of this is 1, therefore this is supposed to be 0. So the limit of this is just a 0. Yes. For those who have already done L'Hopital's rule, you can just take the derivative of this. The derivative of this is going to be sine, and then the derivative of this is going to be cos, and then now cos of 0 is 0, and then divided by 1. You're still going to get a 0 either way. But that's how you solve this if you don't know yet how to deal with that. Another limit will be find the limit or evaluate the limit as x approaches 0 of sine of 3x divided by sine of 4x. I don't know how to deal with sine of 3x and sine of 4x, but I do know how to deal with the limit as x approaches 0 of sine of 3x divided by 3x. I want what is inside to be the same as what I'm dividing with here. But the issue that I actually have now is that I actually did not have this 3x here. I did not have a 3x. So I have to both divide and multiply so that I can cancel it out. I'm left with that. And secondly, I can deal with 4x divided by sine of 4x. But the issue that I have here is that I actually did not have a 4x, so I still need to divide by another 4x. So this 4x and that 4x can cancel out. So this x here is gone because of that x, right? And now I end up having the limit as x approaches 0 of sine of 3x. Let me write the steps once more time. Times I have 4x divided by sine of 4x times 3 over 4. This 3 is this 4 is that. This simply means that now I have a limit as x approaches 0 of sine of 3x divided by 3x times the limit as x approaches 0 of 4x divided by sine of 4x, and then multiply by the limit as x approaches 0 of this constant here. Let's face the facts here. Because x is approaches 0, multiplying this function by 3 is still going to pass through 0, which means 3x is also approaches 0. That's clean. Because x approaches 0, multiplying this by 4 means that I still have this function here still approaching 0. Now, take note of this. I am going to change 3x to be t. So I'm going to have the limit as t approaches 0 of sine of t divided by t, because t is 3x. So we have 3x, so it's tt times the limit. I'm going to change this 4x to be t. So I'm going to have t, okay, because these are not the same. I'm going to have k approaches 0 of k divided by sine of k times the limit as x approaches 0 of 3 over 4. Now, I have something inside which is the same as what is in the denominator, which is the same as that. This limit here, I know it is just 1. I have this thing here which is the same as what is inside there, and I have a sign, and I know this limit. Whenever I have a limit of this kind, I know that it's supposed to be 1. And then the limit of a constant is always going to be that constant. Hence, I have 3 over 4 as the final limit. So that's how you end up dealing with this final limit here. Now, let us talk about this now. Right? Let us talk about this now. This one, we want to find the limit as x approaches 0 of e to the power x minus 1 over x. So in this particular case, again, I will try and make sure this is short. Hopefully you will understand even though it's short. So we have this one here, and it's the last thing that we'll cover, and then we'll go to continuity. We'll go to continuity and focus on continuity and make sure that we do as many examples as possible. So in this particular case here, I will say this once and again. So I don't know how to plot this whole thing, but I do know how to plot e to the power x. And 0 is here. So e to the power x is an exponential function that looks something like this. Yeah, it looks like this. Yeah, it might not be perfect, but it looks like this. This is y is equal to e to the power x. It is an exponential function. Remember this value. If this value is greater than 1, we're going this way. But if it's less, it goes this way. But at this point here, I know that it is, the value there is 1. Now, whenever I want to use the squeeze theorem, because here there is only one way, because we cannot rationalize this. Once we rationalize this, we'll get something that still have another e, and we cannot factorize it. So we're left with the squeeze theorem because L'Hopital's rule, we don't know it yet. If we knew, then we're going to deal with it. Now, let's look into this thing now and see what we can actually do. I know how to deal with this function, and I know how to draw this function that it passes through the origin. But looking at the nature of the squeeze theorem, want this whole function to be in the middle of h of x and some g of x. such that the limit of this and the limit of that is the same. In other words, these two functions need to actually be passing to one point close to x is equal to 0. So I want the two functions that will actually pass through this point so that the limit conditions are met. So I'm going to start with this one that is in the denominator, y is equal to x. What do I need to do to this function that is actually passing through the origin so that now it does not pass through the origin, it passes through that point? I need to add a 1. Hence now the new function is going to look something like of this kind. And now this function of ours is going to be y is equal to x plus a 1. So that's the function that we have that is bounding this function here. The second thing that I need another function that is also going to pass through this point, but is always going to be above this this function here. So there are several other functions that we can think of. One function that I will think is going to be y is equal to x squared plus x plus 1. I think this function can also help us to be one function that is above this whole thing. Another function will be, we have different functions, but now what I actually want us to do, checking on the notes, you will find out actually that we do have a function that we can use. We have several, but I want us to create a function out of this function here so that we can see the function that I think when you wanted to prove that actually this is equal to 1, that function will be a function that is easy for you to remember. If let's say I'm gonna pick a point here which is 1. If I were to take a function, I'm going to say this function is y is equal to 0.5 times e to the power x. Having this is going to take the value that I have here, right, and then take this value and place it here about if I multiply by 0.5, it's going to take whatever the value that I had here to about half, because we are actually shrinking that particular function by a certain by 0.4, shrinking it to about half, which means we are actually compressing it by a factor 2. So this is actually not going to be a good function because I want a function that is going to pass through that point here. So I cannot have this nice thing here. If I am adding a 1 out of this, it's going to move by 1, so it's going to be 1 plus half, so it's going to be somewhere there, so it's not going to pass through there. So I want a function that is going to pass through that 0 but above, to be above this everywhere else. So what if I am taking y is equal to x times e to the power x? Let's look into this. Whenever I am multiplying by a function, okay, let's suppose now my x here is 0. So multiplying this point by 0 will be here, but adding a 1 will actually place this point exactly here. So if I am choosing any point x that is actually less than 1, it's going to take this function and shrink it to that factor, and then after that I add a 1. This value that I'm going to get, because it's above 0, adding a 1 will actually give me a point that is way above. So as long as I pick a value in between here, I'm gonna get a positive value in this portion, and also at the same time when I'm adding a 1, I will end up getting a value that is above there. The question is, how do I know? You can, let's say, take 0.5. if let's say I'm taking 0.5 here and I'm plugging it here, I will get half of the value of this function that had. And now when I'm adding a 1, I will get this is going to be the half of that value and then plus a 1. So that 1 is actually, I have a half of this value somewhere here, and when I have a half of this, adding a 1 will actually, this is 1, so half will be somewhere here. Adding a 1, I will end up getting a value that is somewhere still close, but it's going to be there. You can try that even with a calculator here, and you can say that what if I have 0.5 e where's this? This is going to be e. I'm gonna put an e, and then I'm gonna raise it to 0.5, and then I'm gonna add a 1, and then I will end up getting 1.82 blah blah blah. But if I am getting e, if I'm getting e and then I raise this to 0.5 alone, I will end up getting a value 1.64, which is less than that value. So this function is always gonna be less than that. Another way to look into this, if you don't like it, one thing you can do is, if you look into this function here, I'm gonna say x times e to the power x plus 1, and I'm gonna subtract this value here. So I'm taking this function and I'm subtracting that function from it. If the difference is going to be positive, then it means that this function is bigger. So how do I end up doing this whole thing? I end up saying I'm gonna end up having e to the power x, and then inside here I will end up having x minus 1, and then outside I have a plus 1. Right. So if we look into this here, every time I'm picking here, let's say I'm picking an x here, I am actually picking an x here, you will find out actually whatever this value that I'm actually going to get here, multiplying that, it must always be less than this 1. In other words, it's going to be, we'll end up having a positive value. Right. Let's look into this in another way. Suppose that this value here we had a 1. Remember that this function is increasing faster as we're increasing the value of 1. So if let's say now I'm picking a 1 here, e, I know what e is, and this thing here is saying my e is going to be, if you look at the e alone, this is the value of e. You're supposed to know it. This is 2 something. Multiplying this, let's say I pick a value somewhere here, x is equal to 1. If x is equal to 1, I know that this part here is going to be 1. 1 minus 1 is 0. This is going to be 0. This is going to be 1. So at this point, I get a positive value 1. So I'm going up. So whatever this function is going to be here is going to be actually increasing faster and faster compared to this. This is y is equal to x times e to the power x plus a 1. And then this side here, of course, is going to go like this, but it's always gonna be above that. So that's what this function is going to actually be. Why am I saying this is going to be like this? Whenever I'm plugging a negative value here, right, this one here is going to be negative, right? So I'm gonna get a value here, multiplying by a negative value is going to be below, right? But while it's still below, it's going to be a little bit closer and closer there. And as it is closer and closer there, adding a 1 is actually jumping it a little bit up. So that's what is actually happening here. Another way to look into this will be, what if I were to just increase this to the negative direction? This function here is going to actually increase faster compared to this. So this is actually going to 0, but this one is shifting that value close to that portion there. So now that you have this function, what is nice is that I know that x plus 1 is less than or equal to e to the power x, and e to the power x is less than or equal to x e to the power x plus a 1. So if I subtract a 1 throughout, I will end up having x is less than or equal to e to the power x, and then I subtract a 1 here, less than or equal to x e to the power x, and then in this particular region here, I will end up, this 1 will be gone when I'm subtracting a 1. And then now, if you look carefully into this, what is actually going to happen here is this. Here we will end up saying that if, let's say, x is greater than or equal to 0, then I can divide through and end up getting 1 is less than or equal to e to the power x minus 1 over x, and x less than or equal to e to the power x. The inequalities are not going to be reversed because x is going to be positive. And when I'm taking the limit as x approaches 0, greater or equal to 0 means we're on the right hand side of 0. Of 1 must be less than or equal to the limit as x approaches 0 on the right of e to the power x minus 1 over x, and this must be less than or equal to the limit as x approaches 0 on the right of e to the power x. The limit of a constant is that constant. Limit as x approaches 0 on the right, and then the limit of this is what we're actually trying to figure out here. And then the limit of 0, I can plug it in, and then e to the power 0 is just 1. So I can conclude now that the limit as x approaches 0 on the right of e to the power x minus 1 over x, and then this is supposed to be the same as just 1. Now doing the same now when x is less than 0. So if I have x and x now is less than or equal to 0, I know that this implies that I already have 1 plus x, or let me write it the way it was. X plus 1 is less than or equal to e to the power x, and this is less than or equal to x times e to the power x plus 1. And then, of course, I will end up having x less than or equal to e to the power x minus 1 less than or equal to x e to the power x. Dividing by x, I will get 1 is bigger or equal to e to the power x minus 1 over x bigger than or equal to e to the power x. Why? Because I am dividing by a negative value, so the inequality is reverse. And of course, when I'm taking the limit as x approaches 0 of 1, it must be greater or equal to the limit as x approaches 0 of e to the power x minus 1 over x must be greater or equal to the limit as x approaches 0 of e to the power x. What is important is that less than 0, we're on the left of 0. Now, after looking into this here, this part here, you will find out that the limit of a constant is always going to be that constant, and this inside here is what we're still looking for. I'm going to write it as it is, divided by x, and this one must be greater or equal to, I'm plugging in here 0, will end up having a 1. Therefore, by the squeeze theorem, the limit as x approaches 0 on the left of e to the power x minus 1 over x must be equal to 1. And also note that because the left and right hand limit are equal to 1, then the limit as x approaches 0 on the left, on both sides of e to the power x minus 1 over x must actually be equal to a 1. That's all there is to this part here. I will try and create another video on this, on other different functions, so that you can get familiar on actually picking the functions. This one is coming from the fact that every time you are picking a value in between here, you are actually shrinking this to about a certain fraction of it, and then adding a 1, you're always going to get something that is above this value here. You can even try and plot it. You will see, test it with different values, and then on this side, of course, you'll find out that even though this is negative, it is negative, but this one here, what it's actually doing is actually saying, okay, the more this one is getting more negative, this one is actually trying by all means to shrink it, in this sense that you end up getting something like x divided by e to some x of some sort, because whenever I have a negative here, I will end up having 1 over e onto something that is positive. So as much as this is getting bigger, this one is making it even smaller, and this one is faster than this one. So this one is increasing faster than x, therefore this one will be insignificant compared to that. This one is always gonna be lower than this. So if this one and that one are very lower, adding a 1 will actually give me a value that is actually above that, because I will get a value that is actually above this function here. Hence I end up getting that. Someone else might have decided to use different functions, hyperbolic functions. Y is equal to 1 over some x, let's say minus p plus some q. Someone might have decided to end up engaging y is equal to ax squared plus some bx plus c. These functions can depend on your choice. From different times, I might give you a different, maybe if I get a chance, give you different functions on how you can use these different functions, because the main goal here is to make sure that you pick the right functions. We'll end this lesson, but it's longer. Hopefully it's also fruitful to you also. Thank you.